All right, so now we're going to solve equations. First, let's talk a little bit about what an equation is. So we've done a number of lessons in a row dealing with expressions, and an expression could be written as something, for example, 2x plus 3. That would be an expression. Another way to write an expression might be 6 minus 4y plus 8. That would be another expression. And some other expression could be as simple as 2 plus 4. So in evaluating, remember we used to evaluate expressions. In evaluating this expression, we would look to see, using order of operations, is there a way to simplify this? And 2x plus 3, that's as far as I can go. I can't combine the 2 and 3 to make a 5 because 2 has an x on it and 3 does not, so they're not alike. They're not like terms. This second one, though, could definitely be simplified. I could use the commutative property of addition to switch 4y with 8 and write instead 6 minus, well, I'm going to switch the 8 out front. It has a plus, so 6 plus 8, and then minus 4y would go behind. All I did was switch those two. It's totally allowed. And now I can combine 6 and 8, and I get 14 minus 4y, which puts me in exactly the same place I was before. 4 and 14 can't be combined because they're not like terms. In this third case, I don't have to do anything to evaluate it. I just add 2 to 4, and I get 6. So these are evaluating expressions, but they're not solving anything. We're not in this case finding out what y equals. Notice when we're finished, we don't know what y is. We just know that we have an expression containing y. And in this first case, we don't know what x is or stands for. We just have an expression. Now, I could say, well, let's take the first one and let's let x equal 1, in which case you would just plug in a 1 for the x. And then 2 times 1 is 2 plus 3. That would be 5. But that's still evaluating. Well, I didn't actually leave myself room to write that, so I'm not even going to write it. So we are going to start looking at cases where x has a specific value or y has a specific value, and we're going to use solving equations to do that. So let's look at a simple expression. Let's say x plus 3, and then turn it into an equation by making it equal to 9. Now that it's an equation, it's really sort of a balance. You've seen this analogy in middle school or in elementary school where a balance is made, and on one side is x plus 3, and on the other side is 9. And as long as the scales stay even, then you know that the equal sign represents both sides being the same value. Since both sides are the same value, x can only be one thing. If I were to choose to let x equal 2, for example, I would have 2 plus 3 equals 9. 2 plus 3 is 5 equals 9, and that is clearly not true. X in this case couldn't possibly be 2 because the equation or the balance of the two sides of the equation is thrown off. I want to know what would x have to be in order for x plus 3 to equal 9. Well, obviously, if x were 6 plus 3 equals 9, well, 6 plus 3 is 9 equals 9. So in this case, to solve this system, I would have to discover that x equals 6. Now I did this time in my head because x plus 3, what would x have to be? 6. Pretty obvious, nothing more to do. But we're going to start developing skills that help us solve equations when they're much more complicated than this. And we're going to start with things that are simpler, but we're going to learn tools that will work in the more complicated numbers. So in this case, instead of thinking to myself, what would x have to be for this to be true, I'm going to use a method, an algorithmic method, to solve for what is x when x plus 3 equals 9. So solving equations isn't just finding the answer, it's using specific algebraic steps to get to the same value or to find the value of the unknown variable. to begin to develop these processes, we're going to look at something called an inverse. And you've sort of seen inverses before. Remember 3 over 1 has a reciprocal of 1 over 3, that if you flip a fraction over, that's a little cartwheel, if you flip a fraction over, you get the reciprocal, sometimes called the inverse of the fraction. We're going to use something that's similar, and we're going to use this directly, not very long from now, but for today we want to look at another sort of inverse. And the inverse that we want to look at is by addition or subtraction. So in addition, or I guess I should put addition and subtraction, inverses are opposites. So 2, right? 2 is a number. The opposite of 2 is negative 2. If I add the opposite, I'm going to get 0. 2 plus minus 2, well, the plus minus becomes 2 minus 2, and 2 minus 2 definitely equals 0. And so I'm using inverse properties of addition and subtraction to undo a number on one side of the equation. That's easy enough, yeah? Let's do another example. Let's do a couple of examples of inverses. So we want to look at the inverse of negative 8. So if we have the inverse of negative 8, what happens if I have negative 8 and I add to it the opposite? So remember, in addition and subtraction, the inverse is actually the opposite. So if I have negative 8 and I add to it the opposite number, which is positive 8, what do I get? Negative 8 plus 8 just takes me to 0. So this is the inverse property, or the inverse operation, for addition and subtraction. I think these two examples should be enough since we did a lot of work with these before. So let's move on and do an example where I actually solve an equation using additive inverse. That's what that's called. This is called the additive inverse. It's what do you have to add to a number to make it, to turn it into 0? Well, what you add to a number to turn the number into 0 is the opposite of that number. So let's look at an equation. Minus 4 plus 11 equals, that is so not what we're going to do. Sorry, I was on the wrong page. So we want to solve the equation, or solve for the variable, when we have k plus 22 equals negative 10. Okay, we're going to do two things. One, and let's make a little checklist. We're going to use the inverse to make everything on the same side with k disappear. Okay, so we're going to use inverses to get the variable alone. Because really, solving just means to get the variable alone. And you can see by looking on one side, and alone means on one side of the equal sign by itself. And you can see if I were to put a wall between the two sides, k is not alone. K has a plus 22 with it. So we're going to use an inverse to get rid of that plus 22, and then we're going to use the equal sign to maintain balance. Okay, so what does that mean? First, what would the inverse that gets rid of 22 be? Well, I would have k plus 22 plus, what's the inverse of 22? Negative 22. So the opposite of 22 is the inverse of 22, or it's the inverse operation. So I'm going to actually subtract 22 from both sides, or add the opposite of 22 from both sides. And the reason I say from both sides is if I change one side of an equal sign, if I suddenly get rid of this 3 here, well, this side of the scale is lighter and it's going to lift up, right? It's going to lift up above, not be in balance anymore. So if I were to subtract 3 on this side, I would have to also subtract 3 on this side, and that will bring the balance back into level position. Okay, so here, if I subtract 22 from the left-hand side, then I also have to, Or let me say it a different way. If I add negative 22 from the left-hand side, I also have to add negative 22 to the right-hand side. Once I've done that, I've done this whole thing, this part. I had an equal sign, which meant the two sides of my equation were in balance. I did something to one side. If I do exactly the same thing to the other side, then I'm still in balance. Okay, so let's go ahead and reduce this then. So I have k plus 22 minus 22. Well, those disappear, right? Plus minus 22 is just 0. So I'm left with k equals negative 10 plus minus 22 is the same thing as negative 10 minus 22. So k equals negative 10 minus 22 is negative 32. So first step, I'm using the inverse property to figure out how to get the variable alone. And then the second step is I have to do it to both sides to keep it in balance. So let's do another example. This time we want to solve the equation 62 equals m minus 15. Okay, I'm going to throw in a little step. You don't have to do this step. I happen to like this step. So I like to put my variable, if I draw my little wall, I like to put the variable on the left-hand side, which means I like to put all of this on the left-hand side, m minus 15. Notice I didn't change it. That would be the same thing up here with my scale if I just spun it around, the whole scale. I didn't change what was on the scale. I just rotated it around on the table. Right here, just rotate it around on the table. So I just put m minus 15 on the left-hand side, so I'll put 62 on the right-hand side. So you should be able to see that if 62 is equal to m minus 15, then m minus 15 is still equal to 62. I haven't changed the problem in any way, except I like my variable on the left-hand side. I find the whole problem is easier to work if it's like that. So now let's do our steps on it. Well, what's going to make negative 15 disappear? I'm going to add the opposite of negative 15. So I have m minus 15 plus, let me do that in a different color, plus the opposite of 15, of negative 15. And the opposite of negative 15 is a positive 15 equals 62 plus the opposite of 15, of negative 15. So the part that's new, m minus 15, this is the number, the inverse that's going to get rid of my negative 15, and then plus positive 15 on the other side is the thing that keeps it in balance. Now I can go ahead and start to reduce. On this side, all of this is going to disappear because negative 15 plus the opposite of 15 is just 0. And so I'm left with m on the left-hand side. 62 plus 15 is 77. Now, we want to do something else. Once we get to our answer, we have a way, without turning to a calculator, to discover if our answer is correct. And this is the symbolism I like you to use. I like you to take your answer and draw an arrow back to a big loopy arrow too, back to the original problem. Because we're going to put in, just like we did here, when I put a 5 in, no, where was I? When I put a 2 in for x, and I found out that 2 was not a solution, but when I put in 6 for x, I found out it was a solution because I end up with something that's true at the end. 9 equals 9 is a true statement. So we're going to check using the same method. I'm going to go back to my original. 62 equals, this time I'm going to put 77 in for my m, minus 15, and I'm checking to see if I have the right answer. Is 77 for m the right answer? So I have 62 equals 77 take away 15. 7 take away 5 is 2. 1 take away 1 is, what did I do here? 77. 7 take away 5 is 2. 7 take away 1 is 6. 62 equals 62. That is a correct answer. I know I have correctly solved the equation.